Imagine you need to find the exact length of a room. You buy two incredibly expensive, scientifically calibrated tape measures. You anchor them to the wall, stretch them out, and read the numbers. One tape says the room is 10 feet across. The other says it's 11. You check the tapes, recalibrate them, and measure again. The result is exactly the same. Right now, astrophysicists are stuck in this exact scenario, but they aren't measuring a room. They are measuring the expansion speed of the entire universe, a value known as the Hubble constant. And depending on where they look for the answer, they are getting two completely different numbers. The Hubble constant is the most critical metric in all of cosmology. If you know exactly how fast space is expanding outward, you can run the clock backward to pinpoint the age, the physical size, and the eventual fate of reality. Here is where the math breaks. If scientists use the expansion rate measured from local stars, the universe calculates to be just 12.6 billion years old. But if they use the rate calculated from the early universe, the age is 13.8 billion. This creates a paradox. We have observed stars that are 13 billion years old. If the local measurement is the whole truth, those specific stars would be older than the universe itself. Both of these measurements have been independently verified over and over again. The instruments are flawless. The math is correct. That means our physics is incomplete. Today, cosmologists call this the Hubble tension. To understand the tension, we have to look at how we got those two conflicting numbers. In 1916, deep in the trenches of World War I, a German soldier and physicist named Karl Schwarzschild formulated the first exact mathematical solution to Einstein's equations of general relativity. His work proved that space itself could curve and stretch. A few years later, in the 1920s, Edwin Hubble pointed his telescope at blurry patches of light in the night sky. By tracking a specific type of blinking star called a Cepheid variable, Hubble realized these patches weren't gas clouds. They were entire galaxies existing far beyond our Milky Way. And more importantly, they were all moving away from us. Modern astronomers took Hubble's method and built a distance ladder. Because we know the exact natural brightness of Cepheid variable stars, we can calculate exactly how far away they are based on how dim they look from Earth. To measure galaxies even further out, we use massive exploding stars called Type 1a supernovae, which consistently detonate with a predictable level of brightness. Once cosmologists know the distance of these galaxies, they measure their speed. As an object moves further away in space, the light waves it emits physically stretch out, turning red. By measuring this redshift, scientists can calculate how fast those galaxies are hurtling away. When scientists apply this distance ladder to our local modern universe, they arrive at an expansion rate of roughly 73 kilometers per second for every megaparsec of distance. Initially, some researchers thought cosmic dust might be obscuring the brightness of the stars, causing a math error. But the James Webb Space Telescope recently used its infrared sensors to peer through that dust and re-verify the targets. It confirmed the 73-kilometer calculation with higher precision than ever before. This method has been rigorously tested. The data shows that the galaxies in our modern local neighborhood are pulling apart rapidly. But the distance ladder only looks at stars that exist today. To verify that number, another group of researchers looked at a completely different dataset, the light from the beginning of time. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely for the first time. This ancient light, called the cosmic microwave background, is still visible today. The Planck satellite spent years meticulously scanning these patterns to see how the early universe was structured. When cosmologists plug this ancient data into the standard model of physics, the math governing how dark matter and dark energy should behave, the calculated expansion rate is much lower, just 67.4 kilometers per second. This chart shows how those two rates diverge over cosmic distances. A difference of about 6 kilometers per second might seem small, but at a distance of 3 billion light-years, that gap means an extra Earth's width of empty space is appearing every single second. We have two flawlessly executed, decades-long scientific measurements of the exact same universe that completely contradict each other. Since measurement errors have been systematically ruled out by our best telescopes, the source of this tension likely lies in the physical nature of the cosmos itself. One explanation is the local void hypothesis. It suggests that our Milky Way and its surrounding galaxies are sitting inside an unusually empty pocket of the universe. In a void, there is less matter and therefore less gravity to hold the region together. This lack of gravitational resistance could allow our local pocket of space to expand faster than the denser, ancient regions mapped by the cosmic microwave background. Some theorists speculate that our local void is being influenced by something outside our known universe, perhaps the gravitational pull of a second overlapping cosmos that is physically tugging on our local space. These theories are currently being debated by research teams across the globe. Far from being a settled matter, the field of cosmology is defined by this unresolved contradiction. To find a resolution, upcoming missions like the Roman Space Telescope and the Euclid satellite will map the distribution of dark matter with new levels of detail. We are also beginning to use standard sirens, the gravitational ripples from colliding neutron stars, as a third independent way to measure distance. Historically, when two sets of data refuse to align, it is often a sign that our current models are ready for an update. The Hubble tension is the clearest evidence we have that the rules governing our universe are deeper and more complex than the ones we've written down so far.